Welcome back for our second example of finding an electric field at a given point for a continuous charge distribution. And so we are going to be looking at number 32, page 601. And I'm going to start by sharing all the tactics and kind of listing those out. And then you're going to do the example and you're going to work right beside me. And I'm going to tell you pause and try this step. And then we're going to come back together. Pause and try this step. We're going to come back together. And the best way to do that is when I ask you to pause, actually pause and do it. Don't just watch me. You will learn much more thoroughly if you follow those directions. So if you haven't already, take a look at number 32 in your textbook. It's page 601. And pause the video right now and take a moment. And I want you to draw a picture of the situation, labeling all the things similar to what you see here. So go ahead and pause the video. Okay, so here are our tactics, all right? So these are the exact same tactics that we used in the example problem that we just did. So we're going to relate our charge element dq to the length. And instead of it being like ds this time, it'll be dl or dx because we've got a length here. Actually, it'll be dx. Then we're going to relate the electric field or express the electric field due at point P due to one of those small charge distributions.
Hello, what you're supposed to.
Okay, that's again Jonah. He's a little squirrely this morning. They're mixing baking soda and vinegar and food colors and all that kind of stuff. Oh, I don't know where my little guy went. Anyway, I don't.
Right here.
Regular pen. I know where my little guy went. I don't know where my pen went. Okay, here's my pen. Sorry about that, everyone at home. Okay, so here's my little DQ, right? Here's my DQ laying on my DX, or as part of my DX, right? So we're going to express the electric field at this point right here due to my little charge on my little length element there. Okay, and so then our next step is going to be to look for symmetry and cancel anything out possible. And you can actually start kind of looking at step 3 before you even start, and I would actually suggest doing that. So the picture that you saw of the arc that we did, notice it had like 3 separate drawings. That's helpful to really look at them. How many times have I told you to draw a picture? A bazillion. This is another situation where you have to draw a picture. So at this point, if you haven't already start drawing a couple of electric fields at point P, right, due to a couple of different charge elements. I would pick ones that are symmetric, so maybe pick this one here that I have outlined, and then maybe pick this one here. Does that make sense? Draw those two.
Mom, it overflowed.
Okay, I'm gonna have to take care of something. I'll be right back. Okay, I'm back. No big deal. We just had a little bit of spillage, but they put something down. It's all good. Okay. So then the next step is going to be to integrate to find the electric field. We're going to use the limits of integration given by the situation. And this is going to look a little bit different than last time, which is why we're doing another example. Again, keep it positive, discard the minus sign, we just want magnitude, and then the last is going to be to replace your charge density, and since this is a line, we are going to be using linear charge density, so we'll be using that lambda with the total charge on the object, right? So we don't want to have the, we want the electric field in terms of the charge, not in terms of charge density. Okay, so here we go. Again, when I ask you to pause, make sure you pause. So the very first thing that you're going to do is your first step. So here I've just kind of got my picture here. You're going to have to kind of suffer through my handwriting, and I'm going to be sorry about that. So let's do step 1. So you're going to relate your charge element DQ to your length element. So pause the video, go ahead and write that out. And here is what it looks like. So we know Q over L is equal to our charge density. That's also dq dx. I'm going to use dx, and you'll see here that up here the length x is between this central bisector out to wherever my dx point is, right, my dq point there. So that is going to be what you are going to add up there, right? So we're going to be adding up our dx's. Okay, so that was our easiest one, our easiest step. So you can see here, unlike our arc, the distance between point P and the charged rod is going to vary with where that dx element is. Are you with me? So I am calling the distance between our line up to that point P, that's going to be our capital R, and that's going to stay constant over time. But over here, you'll notice that since the length varies, like as we vary x going out, our our distance from our dq up to our p is going to vary, right? And so that's going to be the hypotenuse of our triangle. So you'll see I've written that in terms of the Pythagorean theorem, r squared plus x squared square root, okay? So I'm front loading that because the next step is going to be to express the electric field at point P caused by your charge element. So for this little bit right here, you want to express your electric field for this dq at point P. So go ahead and pause the video, do that on your own. All right, and it should look something like this. Now, you're going to notice on this example, I am using 1 over 4 pi epsilon naught right here instead of k. You can put k in there so you have less writing to do. I've just started to use that because we're going to need it eventually. Okay, so remember our electric field is for a point charge is just k times q over r squared. So notice my r, my distance from my point P down here, is r squared, right? So we take the square root away of that since that was our Pythagorean theorem, okay? So there's our step 2. Now, remember before we have to replace our dq with our linear charge density. So we're just going to take this linear charge density and we're going to insert it right here, okay? So we're all at the same spot. All right, so we're ready for tactic 3. We're going to look at symmetry and we're going to cancel anything out that's possible. So you're going to be drawing that picture, which we've already done. You're going to start canceling those things out. And you're going to see I have like a little picture here already drawn that you can see. So what I'd like you to do is I'd like you to go ahead and express that. So go ahead and take a minute, pause your video, and then you're going to express the electric field, only the parts that are actually going to contribute to the electric field. Okay, so if we keep looking, I'm just going to reveal a whole bunch here, and we're going to walk you through each of these little steps. So here's our electric field contributions, and notice our x's are going to cancel out. So this is point P right here. So if you superimpose that on top of your diagram, that point right there is point P. Your x's are going to cancel out since we have some symmetry going on there, so only our y's are going to contribute. And so we've written this in terms of sine of theta. And we know that we have a problem because our variables don't match, right? So if we come back here, we can't integrate yet because we have some variables that aren't matching, right? This variable right here does not match with this variable. But the nice thing about trig is that we can rewrite, can't we? So if we take a look back at our picture, and I'm going to come up here, we have some similar triangles. Here's our angle, right? That's the same angle that's right here. So we can rewrite our electric field in terms of some symmetry of this triangle right here. You with me? So the sine of your angle is equal to your y contribution divided by your hypotenuse. Well, we have a similar triangle up here. We can use the r and the x to do that. And so the sine of that angle is also going to be r divided by the square root of r squared over x squared. You with me? So we're going to replace the sine of theta here with this. Right? Because if we come back up here, here is my r, here is my hypotenuse, and this triangle right here is similar to this triangle. Okay? Okay, so we put that in there, we substitute back in, and we simplify it a little bit. And we end up with this expression, okay? We end up with this expression, and we are now ready to integrate. And you're going to notice I have a little note over here to the side. This is not an integral that you're probably like, yeah, I can do that, awesome, right? Because if we take a look, remember we had to get our dx here matching this variable here, which was why we had to substitute in the r over the square root of r squared plus x squared into the sine of theta so that we could get rid of our two different variables and just be in terms of x. But if you're going to notice down here, let's talk through this equation. We know this is a constant. Hey, how about this guy? Is that a constant? Yep. How about r? Yep, that's also a constant. How about this guy down here? Yep, r is also a constant. This x squared is our variable down here, but we've got to the like 3/2, right? Because we had one whole up here, or we had square root up here. We multiplied it by this down here, so we're going to end up with to the 3/2, right? I hope you're with me there. That's not an integral that I necessarily have on the top of my head. So if you look in your textbook, you've got a table of integrals there that you can use for this. And you're not going to be asked on the AP test to do a really hard integral. Because remember, this is physics, not calculus. You'll probably have to do it on your calc exam, but they're not going to ask you to do super wicked hard calculus in the physics test because they're asking you to do physics, not calculus. Okay, so what I want you to do is I want you to go to that table. I want you to find the integral. I want you to put your limits of integration in to see if you can figure out what limits your integration should be in, and then come back with me. Okay, so these next few steps are going to kind of merge together. I don't know if you've noticed, but I have like your steps written out over here. So we just finished step 3. We're going to be working on step 4, which is to integrate to find the electric field. Okay, so I pulled out my lambda and my r because, hey, they're constants, right? That's what we talked about. And our limits of integration are going to be negative L over 2 to L over 2 positive, right? Because if you go back and look at your picture up here, we're from, if I call this 0, you can call this negative half L to positive half L. You probably could also use 0 to L. I think that would work as well, but I'm wondering if you might have to change how you express some of your other quantities. I'd have to think about that a little bit, so I guess I would hang with me and use this this form that I'm doing here. Okay, so if you take a look at your integral of tables or your table of integrals, you're going to see this format. So your x squared, you have an x up here, you pull an r squared out here, and then we've stepped that up, right? So we're powering up there, since that was a negative 3/2, now it's a negative half, right? We added 1 to that. And so then at that point, you'll need to evaluate it on terms of your limits of integration. My handwriting is a little bit messy here, but algebra you should be able to get through but on your own. If not, you can kind of sort through it. It's not really too awful bad. You're having a hard time seeing the rest of that. Let me get rid of this. Sorry about that. Okay, so I'm just gonna get rid of this so that you can see all of this now. Okay. So I've substituted an L over 2 and a negative L over 2. So you substitute that in for your x value because that's what you were integrating with respect to. And that becomes L squared over 4. That whole squared shouldn't be there. It should look like this. I just made a mistake in there. I apologize. We've got 2r squared because our L goes in here, right? L over 2. So the 2 pops down here. Minus an L. So when you add those two together, you end up with this expression. So we've got 1 over 4 pi epsilon naught lambda r over L over r squared, and then 1 over square root of L squared 4 plus r squared. Okay, so because we have basically half of that here, we add them together to get a whole. We cancel out an r, and then we come back up over right here. So we need to simplify a little bit because we have a complex fraction in our denominator. So I multiply both the top and the bottom by the square root of 4 to get rid of that 4 right there. Do you see that 4? We want to get rid of that 4 right there because this 4 is a problem, right? So we multiply both sides, or the top and the bottom, by the square root of 4, which is also 2, which is where that 2 comes in. And then that becomes L squared on the bottom, and then this becomes 4r squared, right? Because that's, again, in the bottom already, so the square root of 4, that stays a 4 down there because it's inside the square root number. Because you do have to multiply it across the parentheses, treat that like a parentheses. And so at this point right here, we are done with step 5. So we didn't have a negative sign, so it's already positive. We're looking for magnitude. We've integrated to find the field. We are ready to replace the charge density with the total charge per object length. Basically, we're going to take this lambda and we're going to multiply it by Q over L, right? Our total charge over our total length, just so that we can rewrite our electric field in terms of our original value of Q and not our charge density. So we substitute that back in right here for our lambda, and we do a little bit of simplification, not much. Our L's cancel out, and we have arrived at our electric field Woo woo! All right, good job. I hope that didn't cause you too much heartburn. Try these on your own. Try them a couple of times on your own until you get comfortable with this process. Good luck. You have an assignment. It is posted on Canvas. So after you've done these two with me, then you should be able to do this on your own.